Hey guys, in this video we're going to take a look at energy and electrons. We're going to be using the equation for the speed of light, which is frequency times wavelength, and we'll also be using Planck's constant to find energy. So let's take a look at some definitions before we get into this. The photoelectric effect refers to the emission of electrons from a metal when light shines on that metal. Some other definitions that we need is quantum. A quantum of energy is the minimum amount of energy that can be lost or gained by an atom. And photon, which is a particle of electromagnetic radiation that has no mass at all, but it carries a quantum of energy. The energy of a particular photon depends on the frequency of that radiation. So our equation is that the energy of the photon is equal to Planck's constant times the frequency of the photon. So another way to just write out the equation, E, energy, equals Planck's constant times frequency. And down here you'll see we have a picture of our electromagnetic spectrum. Okay, and right here in this section is this little piece, this little sliver of visible light, which is what we see. So let's come down here to this frequency. Okay, so we're at 10 to the 7th, we're talking about 93.7 megahertz, which is a common radio frequency. We can figure out the energy by plugging this value, 93.7 megahertz or 93,700,000 hertz, into our equation for energy. So we have Planck's constant, which is 6.63 times 10 to the negative 34th joules per hertz, times 93,700,000 hertz, and that will give us an energy of 6.21 times 10 to the negative 21st joules. Okay, now remember the speed of light is equal to wavelength times frequency, so frequency can equal the speed of light divided by wavelength. So we can also use the equation energy is equal to Planck's constant times the speed of light divided by wavelength. And you'll want to jot that down so you can use that in the future. So again, just another look at our electromagnetic spectrum. Over here we have gamma rays, we have short wavelength, and as we progress over to radio waves we have a longer wavelength. But we have more energy on this end than on this end. Okay, so if we were to look at blue light has a wavelength of about 450 nanometers when compared to red light, which has a frequency around 700 nanometers. Okay, now if we're looking at the energy, the blue light has an energy that is greater than the red light. Okay, so that's how this electromagnetic spectrum works. Now, how does this relate to atomic structure? Well, we're going to look at the hydrogen atom line emission spectrum. So the lowest energy state that an atom can have is called its ground state. If an atom has a higher potential energy than its ground state, it's said to be in an excited state. So what happened was investigators passed electric current through a vacuum tube that contained hydrogen gas. This hydrogen gas was at low pressure, and they observed an emission that was a characteristic pinkish glow. And so what they would do is they'd take a narrow beam of this light that was being given off, and it was shined through a prism. So if you've ever looked at a prism, like if you hold it up to sunlight, you'll see that the prism separates the colors of the light into the colors of the rainbow. That's where we get Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. Okay, so the prism does it. It can separate the light into all the different colors that make up the light. Well, if we do this, if we use a prism to separate the light from this pinkish glow, we see that it's separated into 4 specific colors of the visible spectrum. And those 4 bands of light are part of what is known as hydrogen's line emission spectrum. So here we see we've got the gas discharge tube, and the light is being shown through this slit, and it's hitting a prism, and when it hits the prism it's separating into these discrete specific wavelengths of light. So we have a red one, a teal one, this bluish violet one, and then a violet one. And we can see what the emission spectrum looks like here. So we have discrete specific lines that show where the wavelength of light is being showed. So Niels Bohr proposes that a hydrogen atom model is linked to the atom's electron and photon emission. So according to the model, the electrons can circle the nucleus only in certain paths or orbits. So like these electrons can only travel around in this ring, and our first shell holds 2 and our second shell holds 8, and our third shell holds 18. Okay, Bohr went on to say that the energy of the electron is higher when the electron is in orbits that are further from the nucleus. So these electrons on the third energy level are going to have more energy than the ones here on the first energy level. Let's take a look at a video to see how this works.
In the late 19th century, scientists observed that a characteristic lavender light was produced when a high-voltage electric current was passed through hydrogen gas. When the lavender light was sent through a narrow slit, then through a prism, it separated into distinct lines of different colors. In 1913, the Danish physicist Niels Bohr proposed a model of the hydrogen atom that explained atomic spectra. The Bohr model introduced the idea of quantized energy states for electrons in atoms. In the Bohr model, the electron moves in circular orbits about the nucleus. According to the model, the electron can circle the nucleus only in allowed paths or orbits. When the electron is in one of these orbits, the atom has a definite fixed energy. While in an orbit, the electron can move to a higher energy orbit by gaining an amount of energy equal to the difference in energy between the orbits. When a hydrogen atom is in an excited state, its electron is in a higher energy orbit. When the atom falls back from the excited state, the electron drops down to a lower energy orbit, and a photon is emitted. The emitted photon has an energy equal to the energy difference between the higher energy orbit and the lower energy orbit.
So what Bohr is saying is that we can give energy to the atom, and it's going to cause electrons to move from one energy level to another, and then as they lose energy and they drop back down, they're going to be emitting light. So this short drop from the second energy level to the first one results in the red light being emitted. A larger drop results in the blue-green light being emitted, and an even larger drop in energy results in the violet light being emitted. And so that's what we see as the emission spectrum on a hydrogen gas tube. So in general, there are two different ways that light can be added or given off in an atom. Energy must be added to an atom in order to move an electron from a lower energy level to a higher energy level. So we add energy by this photon that's added to the atom, and the electron jumps up to a higher energy level. And this process is called absorption. Okay? The opposite is when an electron falls from a high energy level to a lower energy level, and that is when a photon is emitted or given off, and this is called an emission spectrum. So throughout this chapter we're going to be looking at emission spectra. We're going to be talking specifically about the electrons, but use this information to help explain what happened with the flame test lab and to also help you with the spectrum activity that we will be doing in class. Please make sure you write your complete notes down, and you can either upload them into Schoology or you can show your paper copy of notes to Mrs. Benke in class.